Welcome to part 2 of the overview of frameworks. In part 1, we analyzed some of the reasons why hardware and networks have historically improved more consistently and rapidly than software in terms of their cost, their quality, their time to market. We then talked about some of the key characteristics of frameworks that can help to improve their quality and the productivity of application and infrastructure developers who apply them. In this part of the module, we're going to compare frameworks with some other popular techniques for systematic reuse. And we're also going to analyze and examine several different categories of frameworks, black box and white box frameworks. If we were teaching this course back in the early 80s, we probably would have been focusing on systematic reuse as embodied in object-oriented class libraries. If you think about the languages that were available at that time, things like C++, Smalltalk, and so on, and Eiffel, there was a lot of emphasis on developing classes and reusable classes that could be applied in a wide variety of domain-independent contexts. Things like file abstractions, strings, abstract data types like stacks, heaps, search structures, queues, trees, etc. Of course, there's always been a long tradition of reuse of mathematical functions, inter-process communication, graphical user interface classes, and so on. And a class library is basically a collection of these classes that can be reused when you build new applications. Some of the characteristics of class libraries, however, are that the classes are often fairly domain independent. They do pretty low-level things or basic things. Moreover, classes in a class library are often passive. The applications themselves are self-directed, and they call out to methods on instances of those classes to do various kinds of things, like open a file, read and write from a file, do string comparisons, pass messages across a network, and so on and so forth. Moreover, there's an awful lot of glue code that is rewritten over and over again to connect the application business logic with the various domain-independent artifacts that exist in the classes in the class library. And the application is typically responsible for the event loop. These techniques are useful, but they only go so far. So towards the end of the 80s, there was a focus on things called frameworks. We've already discussed how frameworks provide integrated collections of classes, objects, functions, components, etc., that collaborate to provide a reusable architecture for a family of related applications. You can reuse classes and class libraries in frameworks. Frameworks themselves are often composed of many parts of class libraries to do things like search structures, files, strings, and so on. Moreover, the application-specific logic can also use the class libraries. So a framework doesn't completely supersede class library techniques. Instead, it augments it with respect to some of those key characteristics we talked about in the previous part. The inversion of control, which allows the framework or frameworks to own the event loops so they can keep track of the events that are happening and demultiplex and dispatch event handlers to take care of those events in various predefined, pre-registered ways. Frameworks also go further than a class library in providing these domain-specific structures and functionalities. So more of the work is done in the reusable framework, and less of the work has to be done from code written by application developers. This is another reason why people often say that frameworks provide semi-complete applications, where a lot of the boilerplate generic code is done in the framework, and the application developers simply have to come along and customize or specialize framework classes in ways to extend them to do application or service-specific processing. There's a nice set of articles that Ralph Johnson has written over the years that talk about frameworks starting from the late 80s. There's another form of systematic reuse that has become very popular over the past decade, and this is component-based and service-oriented architectures. A component is an encapsulation unit that offers up one or more interfaces that provide clients with access to various services. One of the nice things about component and service-oriented approaches is that there's a bigger focus on black box reusability, the ability to take these individual components, which are sort of classes on steroids, and be able to combine them together into various assemblies through the use of metadata, often, though not always, described using some type of XML. So in some sense, component-based approaches and service-oriented approaches take the more powerful but more complex capabilities of a framework and encapsulate them in a way that's easier for application developers to work on. I've written a number of articles about component-based techniques, which you can take a look at this URL. The main point here is not that one approach is better than the others, it's that there are different approaches that can be applied at different points, and they often work together. So frameworks leverage the capabilities of class libraries, component-based and service-oriented architectures leverage capabilities of frameworks to implement them, and it's the job, as always, of the application developer and the software architects to know which approaches to apply when. When we start taking a look at frameworks more deeply, it turns out that there's a number of different types of frameworks. There are so-called black box frameworks, which really only require understanding of external interfaces of objects or classes or components. And the elements in black box frameworks are typically reused by parameterizing or assembling objects and composing them somehow. An alternative approach is known as a white box framework. When you use a white box framework, you typically have to understand some parts of the framework implementation to a certain degree. That's because you typically end up having to know how to subclass from base classes and override various hook methods. There's a nice paper written by Brian Foote and Ralph Johnson that talk about some of the aspects of black box and white box frameworks that I highly recommend you take a look at this URL. Now, it turns out that black box and white box frameworks typically apply different groups of patterns. A black box framework is often developed using patterns that emphasize object composition, things like the strategy pattern or the decorator pattern. You can find out more about these patterns by taking a look at the website. Likewise, white box frameworks very typically use a different group of patterns, ones that tend to emphasize inheritance-based extensibility through subclassing and overriding of dynamically bound methods. Examples of patterns in this space would be things like template method or state. Once again, you can take a look and find out more information on the web about these patterns, which we'll also cover later. As it turns out, and we'll see an example in just a second, in practice, many frameworks combine both aspects of white box and black box techniques in order to provide the overall extensibility and customization capabilities to application developers. As a general rule of thumb, white box frameworks are easier to develop because you don't have to anticipate as many of the different use cases. But as a result, they're also somewhat harder to use because you, the application developer, have to understand more of the implementation details. Conversely, black box frameworks are harder to build because you have to anticipate more of the canonical interactions and use cases and interfaces. But they're also typically somewhat easier to use. And oftentimes, you don't even have to understand many aspects of object-oriented programming in order to be able to use a black box framework, because you're really plugging or composing various kinds of objects as plugins in a more binary black box kind of way. Let's take a look at some examples to make white box and black box frameworks more concrete. The particular example here goes back to one of the motivating examples we gave when we did the introduction earlier in the module about the Gang of Four and POSA patterns, where we talked about the use of Android to allow us to build an application where we could download images from a web server across a network. If you were to take a look at the implementation of such an application, you might find the use of a nice framework that's provided by Android called AsyncTask. AsyncTask is a framework that is exposed to application developers through a facade class called AsyncTask. And this facade class has some interesting characteristics because it embodies both white box and black box framework techniques. We'll first look at the white box aspects. You use AsyncTask in order to be able to offload from the user interface thread some long-running operation or operations. If you don't do this kind of thing, then it's possible for your application to get the application not responding exception because the user interface thread may be blocked for an extended period of time. So the AsyncTask framework helps to offload this work in a convenient way. Here's basically how it works. There's a template method called execute defined on AsyncTask. And you call execute and you pass in one or more parameters. And the framework then takes over and it runs something called onPreExecute, which is a hook method that's used to initialize some processing in the user interface thread. And then it goes ahead and the AsyncTask framework turns over the operation to run to a background thread. And it calls back on a hook method called doInBackground that you have to provide. And that operation runs in a separate thread, separate from the user interface thread. So if that thread blocks for a long time, not a problem. You're not blocking the main thread of control. And that thread can do various kinds of operations. It can post progress updates to the main thread. And when it's finished processing, however long it takes to run, it can return the results back to the main thread where the onPostExecute method is invoked, which does things that require the main thread of control, such as displaying an image. You can take a look at the Android website to find out more information about AsyncTask. One of the characteristics that makes AsyncTask a white box framework is the fact that you have to subclass from AsyncTask. AsyncTask is a base class. It defines a number of interesting pieces. It has some generic parameters that identify the type used to run in the background, the type used to indicate progress, and also the result of the doInBackground method when it finishes executing in a separate thread. It has a template method called execute, which arranges to call the various hook methods onPreExecute, doInBackground, onProgressUpdate, and onPostExecute at various points. And you can come along and subclass from AsyncTask and fill in any of those hook methods as you desire. Here's an example of overriding the methods in our simple downloading activity example we talked about. The onPreExecute method's called back to set up a dialog box to show that downloading is in progress. That runs in the main thread. The AsyncTask framework calls doInBackground, which goes ahead and downloads the image across the network from a web server somewhere. And when it's finished, it passes the result back to onPostExecute, which turns around and displays the message and dismisses the dialog. Here's an example of actually using this white box framework, very simple example. You create an instance of download AsyncTask, and then you go ahead and invoke the template method to start all the various parts of the framework in motion. And you can only declare an individual async task once, and it runs for however long it takes for doInBackground to finish processing, and then it wraps up. Let's now take a look at how the AsyncTask framework in Android also has some black box characteristics. So we saw the white box characteristics where you have to subclass from it, but there's also some interesting use of black box characteristics as well. It allows you to be able to control the number and behavior of threads that run in the background, carrying out all the various work run by async tasks. So here's essentially how this works. So what you can do is a client, such as our download activity or other activities, can select the desired executor. An executor is basically an abstraction for multi-threading, and you can select a number of different strategies to use. You can select a serial executor, which is the default behavior, or you can select a thread pool executor, which allows a pool of threads to run different async task execute operations in parallel. In fact, you can even go as far as to write your own custom executor and pass that in. And that allows the framework to run different do-in background hook method invocations in different threads of control, so they can run in parallel. The executor is treated as a black box by AsyncTask. You don't have to subclass anything in order to be able to plug in the pre-existing executors. If you make your own executor, you subclass from executor, but not from AsyncTask. So the AsyncTask framework remains a black box. And to use it, you only have to understand the external interfaces, such as the execute method that you would fill in on a custom executor that you might implement. And the executors can be plugged in as strategies. So once again, we see the use of the strategy pattern for the black box part of AsyncTask, and we saw the template method pattern being used for the white box part of this particular framework. So you can see AsyncTask is a nice example because it illustrates both black box and white box techniques being used within the same framework abstraction. If you're a C++ developer or not a Java developer, take a look at the paper at this URL. We have something that's part of the ACE framework that we'll talk about later called the strategy acceptor. And the strategy acceptor is a nice example in C++, as described in this paper, that illustrates the use of white box and black box techniques for the acceptor connector pattern. So to summarize this part, frameworks are very powerful, but can also be a bit complicated to build and use. And that's due for a variety of reasons. You have to understand object-oriented programming oftentimes, unless you stick very, very closely to black box techniques. You'll often have to use inheritance and dynamic binding and so on. And of course, there's the key issue, which is the inherent and accidental complexity within the application domains themselves. That's where the real complexity comes from. A framework is embodying much more sophisticated roles and responsibilities and structure and dynamics and so on. One of the ways to try to alleviate this complexity is by understanding patterns, in particular pattern sequences and pattern languages, which help to guide us and justify and motivate why we build and why we apply framework pieces, components, objects, classes, and so on in the way that we do. And you'll see lots and lots of examples of this as we go further on throughout the course. If you take a look at this URL, you'll find some examples of how we used patterns to document the frameworks that we used when we built some of our communication middleware in Corba. Because of the complexity of building frameworks, it's often better to try to use or customize off-the-shelf frameworks rather than trying to build them entirely yourself from scratch. You can do it from scratch, but that requires people with a tremendous amount of knowledge of both the domain as well as object-oriented programming techniques, and that's sometimes hard to find. Other kinds of approaches, class libraries, components, service-oriented approaches, and so on, are often somewhat easier to use than frameworks, but they don't typically provide you with quite as much power or flexibility. It's kind of like a knife and a fork and a spoon are simple, easy to use utensils, and you can do lots of useful things with them. But if you really want something that's more flexible, you may have to use a more complicated device, like a Swiss Army knife of some type that allows you to do many more things. Because of the complexity of frameworks, successful software projects often apply what I call the funnel approach to developing and applying framework technologies. The funnel approach typically works by having a core set of people that are going to either build or more likely take off-the-shelf component frameworks and then customize them for the particular needs and uses of the application developers that they support. So rather than trying to build frameworks as a big effort by all the people on a big team, you have a small group of people who have that expertise in both the domain and in the lower level patterns and pattern languages and object-oriented techniques and so on, taking, either building or customizing frameworks, and then exposing these frameworks up to the application developers through more simplified facades, such as components. And then the application developers themselves can work with a simplified form factor of components, often plug and play, using scripting languages, perhaps using simpler languages like JavaScript, when the complexity is then pushed down to the smaller number of people who maintain the underlying infrastructure. There's a paper I wrote a number of years ago that talks about different ways of applying frameworks, and it evaluates the pros and cons of different approaches. And I encourage you to take a look to learn more about how to apply these techniques for your purposes.